Okay. Last days will be on structure formation, how you perturb the homogeneous universe to get what we will call dark matter halos and galaxies and things like that. And how do you relate the two together? So these are so one here means the background evolution. We'll try to explain what that is today in rough terms. The best book on very elementary on background evolution, focusing on a Newtonian formulation, which we will also focus on, is this. If you want a general relativity pedestrian introduction, there are lecture notes by Pedro Ferreira, which are quite nice. General relativity for pedestrians, and which explains some basic things, and also how you can get evolution, background evolution of in cosmology from the FRW metric. We will discuss the Friedman-Robinson-Walker metric, and we will just have one slide on how you get it from GR. If you want to try it yourself, you can check the lecture notes by Pedro Ferreira. They give examples of how this, well, an outline of how this could be done, or you can do with Walid Hanafi also with the GR tensor, like you did with the Schwarzschild metric and the Toph metric and so on. You can do also with the FRW. So these are a bit more advanced. The book by Peebles is old and a bit outdated, but of course Peebles is a very smart guy, so it's still a useful book to look at. Weinberg on cosmology is very advanced, but the first 100 pages or so are quite nice and follow what I'm trying to talk about here. After that, it gets very advanced and not standard introduction to the subject. So I don't recommend after the first 100 pages. This is an intermediate level text, okay? So what is the subject matter of all this stuff? If you type cosmic history or cosmic evolution or things like that on Google, you'll get things of this type. It tells you something about the modern day or the contemporary, present day idea of what we think how we think cosmic evolution happened. So in the very beginning of the expansion, it's supposed to be, did you get to inflation, Alexei? You didn't. Okay. Alexei will talk, I guess, tomorrow about inflation, where there are fluctuations in the quantum field of the sort that Syed was talking about. And that produces the fluctuations in the quantum field that are really emanating from Heisenberg's uncertainty principle are stretched into the classical regime and produce fluctuations in metric or in the potential, and the potential fluctuations produce density fluctuations. This we will talk about on Wednesday and Thursday. And they're supposed to produce galaxies and so on. Before that, the universe is very hot because it's compressed, it's expanding, and it's a plasma. After about 400,000 years, where we will really start, the area before is interesting, and I used to give talks about it. And if anybody is interested in we can talk much about it too. The thermal history between the quantum fluctuations and the recombination. This is called the recombination era. Is interesting in that, along with inflation itself, is a laboratory for fundamental physics, because it's very high energy that accelerators on Earth cannot. You need an accelerator of the size of a galaxy to get to the scales that are not the size of Geneva, over 27 kilometers, but the size of a galaxy to get to the scales we are talking about in the first few seconds here or so on. Okay? So this is interesting. The very early part of the cosmic history is interesting from the point of very high energy physics. Not talk about it too much, we'll start mainly here at recombination, where we can see the radiation left from the cosmic microwave background, which is about a few electron volts here or something, 3000 Kelvin, but it has been redshifted, expanded to about 3 Kelvin, 2.7 Kelvin or something. When we see it here, we are here. And in between, things start to form. We'll explain why they form, which is a property of gravity. And they evolve, and one of the big projects, so to speak, endeavors in the past decades, and even more so in the next 10 or 20 years, is to map the density of galaxies, their properties, and so on, with cosmic evolution, to test our models, starting from quantum fluctuations and all the way to today. So, by mapping our model and comparing with observations, okay? So this is something that is very big in the next few years or next few decades. Okay, but we have to start with what we're talking about, really. So what are the distances? If you are going to the moon, you are 1 light second away. Okay, so the light takes about 1 second to go from the moon to the Earth. That's why the Apollo astronauts can talk to each other. If it was 1,000 light years, they can't. Okay? If you're going to the sun on a light ray, then you take 8 minutes. The nearest stars are already a few light years away. Okay? So the nearest stars, like the sun, more or less, are a few light years away. They have names because they're very old, in the sense that discovered a very long time ago. Okay? Most of the other stars in the universe don't have names, of course. There are too many. There are too many galaxies. There's more galaxies than people who ever lived. And each galaxy will have like millions to hundreds of billion stars and so on. Hundreds of millions. Now, but we don't use light years in astronomy. We use something called a parsec. What is a parsec? A parsec is how far you need to go for the orbit of the Earth around the Sun to look 1 arc second. What is 1 arc second? Is 1 over 60 over 60 of 1 degree. A circle of 360 degrees. A minute is 1 over 1 over 3, 1 degree. And a second is 1 over 60 of a minute, like in time. Okay? Also for historical reasons. So this is a parsec, which is 3 1/4 light years or something. Okay? So you see, this is already 3 1/4 light years, which is like the nearest star. Already, not the Earth looks small, the orbit looks like 1 over 60 over 1 over 60 of a degree. And that's already the nearest star. So, and then you're going to talk about kiloparsec, megaparsec, gigaparsec. You know, so this parsec is tiny in cosmological terms, but it's actually huge. It's how far you go for you needing to need a big telescope, really big, in fact. In fact, better than anything we know, almost, to see. No, I mean not better, but yeah, a big telescope to see the orbit of the Earth. Then, if you've been in a clear night in the desert, you'll see a band of light. With the naked eye, you can see it on a nice clear night in the sky. Not the individual stars that we have names on, but a diffuse band of light. And that's the disk of the Milky Way. This is the galaxy we are in. This is another galaxy that we can see, not edge on. We see the Milky Way as a band because we are in it. We are in the disk of the galaxy. So if you're in the disk and you see it edge on, you see it as a line. Okay? This is another galaxy similar to the Milky Way, maybe Andromeda, so I don't know. It's another galaxy, I don't remember which one. That is similar to the Milky Way being a disk, but is seen not while you're in it, but outside. A galaxy is already we are 8 kiloparsec already. This parsec, we are already 8 kiloparsec means 8,000 parsecs from the center of the galaxy. So we are not in the center, we are like something like 25,000 light years or something, 8 kiloparsec away. The stars you can see with the naked eye are about 1,000 light years away. After that, you need a telescope. But you can see the band of it. This is already quite big. Now you have many different sorts of galaxies, and we'll speak a bit about them in the next few minutes. Some of them are like the Milky Way, disks and spheroids, they are rotating. Some of them look much more like spheres, and there are many in between. And some are merging, and this is quite important for testing the cosmological model, as you will see later. The merging, some of the galaxies are merging and colliding, and this is important. And it is believed that when you merge two like that, you get this. It's like breaking eggs, or breaking something that is fragile, like this one, and improbable. You get them together and they make a random motion. So from rotational motion to random. When they collide or otherwise, you find a lot of. Now this is made of stars. Galaxies are made of stars and gas and something else that should be there. In present day universe, the galaxies are 10% gas and 90% stars of the visible material. Earlier in the universe, we observed that it's much more gas, and this is also an interesting test of what's going on. When they merge, the gas gets perturbed, and there are many different ways, but this is one way. When they merge, the gas gets perturbed and driven to the center by torques, by non-axis symmetric torques. It's driven to the center, and it feeds active nuclei in the center, or feeds starbursts, star formation that is very quick. Okay? So this, for example, was Edwin Hubble's classification. Those of you who took talks on Mahmoud and so on probably know it by now. So these are galaxies like the Milky Way. This is flatter than the Milky Way. This is a bit more, with a bulge. They call it a bulge. فيها كرش في الوسط bulge. And these are the elliptical. Some of them are spherical, some of them are flattened, but they have large random motions. These are rotations, these are random motions. Some have bars, those, like, not bars where you get the bench, it's bars, okay? Bars, عصاية. Okay? Now Hubble thought that this, if you want to ask why they have bars and so on, we can talk about it all day, because I did my PhD in things similar a long time ago, but I'm following a bit what's going on. But it's not central to our argument. Although it's a test also of cosmology. When do bars form? When can a disk support a bar? These are also tests of the cosmological model. But it's too detailed to get into in our lectures. Okay? Now you can produce this. Now Hubble thought it's an evolutionary sequence. Like he thought that these guys, for example, evolved into these guys. And some people thought it's a reverse. It's evolutionary from these guys to these guys. And I actually, when I did my PhD, I wanted to prove things like that. But I was very naive. But you can show that some evolution does happen. But in general, it's not like that. In general, it's a far more complicated thing that happens within the particular cosmology. When I started my PhD, galaxy and cosmology were a bit different subjects. We could walk in 50 a lot, you know? You could take your ease. Now, galaxies and cosmology are the same subject, and the thing is very constrained. You cannot, and it's very complicated, but Some people with simulations can actually produce that from the fluctuations in inflation and produce your galaxies. But as I hope will arrive in the last talk, this contains a lot of parameters that they fix and so on. But they can produce your Hubble sequence. Not an evolutionary sequence, but by very complicated ways. They can produce it. This is like the Hubble sequence from observations here, and this is from simulations. You can see they're doing well, but that's another story. Okay? So these are very large simulations. Don't try it at home, huh? These are very big projects. These are really big things that take months on end and order 10 to 100,000 processors, computing power, and codes of 100,000 lines, and so on. And even more. It depends. Okay? So, we also, back to observations, you can also nowadays, Hubble only observed these guys. We can nowadays, or this is even a bit old, this is from the Hubble Ultra Deep Field, like 10, 15 years ago, and you can already see evolution. This is very far away. We're talking about things of the order of a gigaparsec, you know? Very long time ago. Light took like billions of years to come and so on, things of this time. Right? And you can see that this Hubble sequence breaks down. These galaxies at very high, what we call high redshift, or very far away, long time ago, are quite different. They appear, at least by looking, many of them cannot be classified here, and many of them are merging. And this, at least in principle, is good, because the current cosmological scenario says there is finite time, there is evolution, and it involves merging of small objects into big ones. So, if the universe was static and everything was constant in it, you'd expect that this picture should look like that. And this is like the Hubble Ultra Deep Field is like a billion years after the beginning of the expansion. We are 14 billion years. So you expect it to be the same if the universe is infinite age. But if it's not, you expect difference. And we find difference, and that's good. Now, other tests include the mass function. This is the number of galaxies you find within a certain mass range. And this is also from Hubble. I'll talk about the James Webb in the last lecture. This is from Hubble. And you already could see that it fits, the theoretical model fit fairly well, as long as you adjust them, calibrate them, so to speak. Then they fit reasonably well. But at high masses, you already see with the Hubble Space Telescope, there's a slight problem. These are different times. This is like, let's say the relation, this is like 1 billion, 2 billion, 5 billion years, things of this sort. Okay? This is, in terms of redshift, we'll speak about redshifts tomorrow. But basically, redshift is a function of time in our cosmological model. So this is another way of saying time for today. Tomorrow we'll say how we relate the redshift to time. Okay, but we can't do everything at once. Okay, so there may be a problem with big galaxies already in the Hubble data. Much more in the James Webb, and this is a really big thing going on. Is there a problem or not? And if there is a problem, what is it? And so on. But we need to start to having some idea of how do we theoretically model all. First of all, at large scales, gravity governs. Gravity is much weaker than electromagnetism or the other forces. Like if between two electrons, the force or the proton and electron, the force of gravity is like 10 to the minus 30 something, 10 to the minus 40, or I don't remember, but very small number compared to the gravitational force. The gravitational force is a very small number compared to the electrostatic force. So gravity is very weak. But it is long range, like electromagnetism, but unlike electromagnetism, it has it has no positive and negative. So you don't have a divider like in a plasma. You have only attraction. And this causes very different structural properties. Makes them unstable to gravitational collapse, all you heard about black holes and so on is a result of that, and many other things. No statistical mechanics, a lot of complications. Okay? So, but because it is long range and unshielded, meaning no positive and negative, only one attractive force, it wins on large scales. Everything else dies out. The nuclear forces, the small hooks, short range, so they go both weak and strong. The electromagnetism goes because of the positive and negative. You're left with gravity, which governs the universe. Okay, so it's very important. What does gravity do? Gravity makes things, if left on its own, to cluster. Because it's only attractive. So if nothing prevents it, it makes things cluster, makes things collapse. Gravity makes things important point. Okay? Now, why doesn't it make things collapse on their own? Now, this is a gravitational system that is in sort of equilibrium. These guys, like elliptical galaxies, have random motion, so their RMS, or variance, speed, is much larger than their average speed squared. The average speed squared is nearly zero, because it's random. So, these guys, the RMS is about the same as the average, because they're rotating. The average is of the order of the RMS. Right? Mean motion, no mean motion. Now, in general, this is what you get for a system in dynamic and equilibrium, meaning long-lived and can survive like that, like a galaxy. This side, the kinetic energy, equalizes this side, the potential energy. The potential and the twiddle means approximately. This is important in astronomy and astrophysics. Approximately, and estimates and physical intuition to estimates are extremely important, okay? Much more than precision, in my viewpoint. Okay? Because things are usually too complicated for a lot of precision. But, and even if you want to do the precision, you need to do this first before you spend like 10 years doing a computer simulation. Even if so you want to do this sort of thing to understand what's going on, because things are expensive. You know? So this is called the Amr theorem, and I can show you proofs, but it will take a long time, so just take it. That the potential energy is about the same as the kinetic energy. Formally speaking, it would be 2T plus V, 2 kinetic equals 0. But this is good enough for us. They're of the same order. Okay? Right? So this is in zero equilibrium one way, no, sorry, this way, S should go over here. And this is in zero equilibrium because of silsila halakhi. Okay? And an important thing, let's say we are in the room. Does anybody have an idea what's the speed of RMS speed of the molecules in the room here? Air, nitrogen, oxygen, okay, 300 kilometers, which is about the sound speed, right? So let's see what this is in the room. This is, let's say this is a mass 1 kilogram, and this is R is 1 meter, 1 meter, okay? A volume of 1 meter cubed, R 1 meter of volts. Meaning like air is like that, okay? So this here is 10 to the minus 10, about, G, in SI units, okay? Meter cubed and so on. This is 10 to the minus 10, and this is 1 in air, and this is 300 squared. You see the huge difference? So, in air in the room, this is 1,000, and this is 1 over 10 billion. So, the air in the room will not form galaxies. Okay? The gravitation is far too weak. But, let's say we take the air in the room and keep on increasing the volume here, the mass. This will go, M goes with M, this will go as R cubed, and this is as R. There will be an R where the air will form a galaxy. With a very big R. Huge R. You need to multiply by a billion times billion times 10 to the 10 to the 10, 100, 10 to the 4, 10 to the 5, which makes it 10 trillion. So you need to go quite far, okay? With air in the room to form a galaxy. Okay? And this is called a gene scale, where this happens. Because genes derived it, and we'll do it more than once, but this is the most elementary way of finding a gene scale. When gravity becomes dominant over pressure in a gas, if it's a normal gas. Okay? And this is your gene scale, and this is called the dynamical time. Listen, two important things about the dynamical time. This is the time for a particle to cross a galaxy. Mind you, it does not depend on R or on M, but in the combination M over R cubed, meaning it is scale-free. Very important. And it's because the potential is a power law, Gm over R. All power law potentials are like that. It is easily shown. You can do it as an exercise. Like do here, instead of R cubed or whatever, you will find the same. Right? Therefore you get in galaxies scaling relations. So things like, if you go astronomy, galactic astronomy, you see things like atomic fission relation, the Faber-Jackson relation, or a bit more fine Faber-Jackson relation called the fundamental plane. What is this stuff? This is the luminosity of a galaxy and its rotation speed. So, the more bright a galaxy, the faster it rotates, if it's a spiral galaxy. Which you would expect, okay? It is bright, it has more mass, and it rotates faster. And this is for the guys who are in random motion, the more random motion they have, the more luminous they are. And this is also intuitive, and it follows from our very simple relation here. Nice. But the problem is, it correlates. Why does the visible mass correlate with the total mass so tightly when the total mass is actually supposed to be in dark matter? Some people who are into modified gravity think this is evidence for modified gravity. Okay? But we won't discuss too much modified gravity here, but if there are questions, you can comment. So how do we know, or we think, there is dark matter or modified gravity? One of the evidence for that is rotation curves of galaxies. But mind you, people sometimes put this as the main evidence for dark matter. People who do galactic dynamics know that this is evidence for modified gravity. The evidence for dark matter comes from after Tuesday, mainly, from the cosmic microwave background and Larson structure. These are very difficult to do in electronic. This one is easy. You have the velocity of rotation of a galaxy like the Milky Way in kilometers per second, and you have R in light years or kiloparsec or whatever. You plot it. You make a plot. R versus V. Or V versus R. And if we take only the mass here, it will start going down. It will start going down because if I fix my mass here, this V will go down 1 over square root of R. V squared as 1 over R. So it should go down, it's like Kepler's law. It should go down as 1 over R. But it doesn't. It keeps on being flat, or sometimes, as in this galaxy, increases. So we think there should be more mass. Now, some other characters. So this is the dark matter issue from the point of view of galaxies. Now, the density of the galaxy, if it's like that, is very small. Air is 1 kilogram per meter cubed, like we said, but the density of a galaxy is incredibly much less. And this is because we have a gravitational equilibrium with gravity. And gravity is much weaker, as Said was saying. There is characteristic scales. with the forces, except that gravity can have more than one scale. But typically, if it doesn't collapse into a black hole, you need densities like that. If the densities are larger, it will collapse into a black hole. How do you collapse into a black hole? We can come to our equation again. If somehow you could decrease your energy by having a gas radiating the energy away, just radiating photons, then it could shrink. And if it shrinks, this could goes to zero, and this goes to infinity. And if it goes to infinity, relativity, this one Newtonian, relativity starts coming in, and you become a black hole. Right? Now, that's why galaxies are not relativistic, because if they were, they wouldn't exist as galaxies. Now, and you'll find that your typical thing determining the Schwarzschild radii and the pressure and so on, the relativistic stuff, is of order of 10 to the minus 6 in mass. So very small. Galaxies are not relativistic. So what is preventing them being relativistic? Well, first of all, they form stars, and stars don't radiate, at least not in the way of radiating and losing energy and making the thing shrink. Because if they did, the whole galaxy would become a black hole. And indeed, that's what probably happens in the very center, where you have supermasses and black holes of 10 to the 9 solar masses and so on in the very center. But in the outside, that doesn't happen. And another thing is that there is dark matter, and the dark matter does not radiate at all. So it keeps a large characteristic, fluffy scale of very small density, which avoids the relativistic limit and avoids things going to singularity. Well, now let's go to bigger scales than galaxies. We already did very far away and small pencil beam, the Hubble ultra deep field. Now we're going to take a large area of the sky and trying to map it. Not as far at all as the Hubble deep field, but much wider. You'll find that there are galaxy clusters. Galaxies can make and have random motion and cluster, make groups. Of 100 or 1,000 galaxies, or maybe the maximum is 10,000, I can't remember, something like that. And these are clusters of galaxies. And they also contain dark matter, and in fact, that's when it was first suggested by Zwicky. It was from the random velocity, v-squared average, of the galaxy clusters, of galaxies in a galaxy. But if you go to a larger scales, you'll find that you tend towards homogeneity. What do we mean by tending towards homogeneity? It means that, let's say, these things are of the order of a megaparsec. 1 million parsec, 3 million light years. This is the size of it. If I start going to 100 megaparsec, 10 or 100 megaparsec, I'll find, this is a picture of the sky in a micron regime, a whole sky in a micron infrared regime, microwave infrared, and 2 mass survey. And this is the galaxy here, okay? So we forget about that. Let's look at the dots. All these dots are galaxies, other galaxies. There are some clusters which they have names, Virgo cluster, Coma cluster, Abel clusters, and so on. There are many different clusters like this one over here. But on scales larger, you'll find that things tend to randomness, to homogeneity. And so if I take a volume or an area here, this is roughly speaking, I take this, and then this, and then this, and then this, and I count the number of galaxies in it, I find that the numbers start to converge. It starts being constant. The fluctuations decrease. Right? So there are surveys for doing this sort of thing. The oldest, probably modern survey, there are older ones like the APM survey in the 1980s, early 90s. But the newest modern one is like from the 20 something years ago, maybe started 20 something. It's called the 2DF survey. So, and the more Recently, the state of the art was a Sloan digital sky survey, SDSS, if you look at things. And this is an example of a picture. This is a picture of the sky. This is the redshift, how far away they are, and this is the angle. And this is the Sloan, like this is already 3 gigaparsec cubed or squared on the projection slice. This is already, we're going to 10 billion light years, huh? Big stuff. Okay? So not like a parsec, but a gigaparsec. Okay? So every one of these things is a galaxy, and they make a cosmic web, which we'll try to explain a bit in the last lectures on Thursday. It tends towards homogeneity on very large scale. This is the Sloan Digital Sky Survey. The state of the art now is DESI. These are ground-based, also connected to the Sloan. And there is space observatories like Euclid, which is already operating, which is doing the same thing. What is the same thing? Maps. Sloan Digital Sky Survey does maps up to redshift 0.3, 0.4, a bit limited in how you, very wide, but doesn't look very long ago. The Euclid and Grace Roman after that, and that's a few years from now, and things like Vera-Rubin telescope, which I think is already starting, will do both wide and deep. And by the way, Vera-Rubin is the first one who discovered the flat rotation curves, and they named the observatory in South Chile after him, and Chile in South after him. Okay, the basic thing about the dedicated telescope, they have special cameras where they can make spectroscopy in one shot over a large area with a lot of galaxies. Dedicated telescopes, they don't do everything like normal telescopes, they are dedicated to certain things, making maps. So the James Webb, for example, does almost everything, but its aperture is small. They cannot make maps easy. These guys are for mapping. Right, and this is the really large scales on all sky radio survey project. So every one of these things is a galaxy, and you can see the homogeneity really clearly coming out, or at least ISO. Project. Okay? So every one of this is a galaxy on extremely large scales, and you can see it's quite clear. And this is like if taking them smaller scales, you find it self-similar, which is another important in this case. So a nice little paradox quickly is why if the universe is infinite in space and infinitely old, why is the night sky not like completely bright? This is from the 19th century, or maybe before, I don't remember. This is all called Olber's paradox. It excited people like the poet Edgar Allan Poe. You know? So why? And this is not true, because if you light, as we will see when we study the velocity distances tomorrow, the intensity of the velocity goes down as 1 over r squared, but the area you are seeing of the sky goes as r squared. So why doesn't it converge to a star? So everything would burn. We would see the whole, we would see everything like the sun. Well, the reason for it is the universe is not infinitely old. So this is very elementary evidence for evolution. And it's also expanding, that's more. Okay, so this is, there are what we will call horizons. Okay? So if it evolves with time, we need to have evolution equations. Properly, so for the whole universe, assuming it's homogeneous and isotropic. Isotropic means it's the same in all direction. Homogeneous means it's the same from point to point. They're not necessarily the same. A crystal in solid state could be anisotropic but homogeneous. And you can have an isotropic but inhomogeneous, like a sphere where the density is a function of radius. That's isotropic but not homogeneous. But if you're isotropic at every point in the universe, then you're homogeneous. And there's now evidence for homogeneity too, because we're looking at higher reaction. Before, when I was your age, it was only evidence for isotropy. And now also the homogeneity is tricky. But yeah, isotropy is certain. So here we go. We're going to take patches that are big compared to this cosmic wet things, and we're going to try to see how they evolve. If we want to do a Newtonian evolution, which we'll do here, and we'll sketch very quickly tomorrow how things can be done with GR, and also you can do it, as I mentioned, with Walid, or you can do it yourself if you call Pedro Ferreira's lectures, if you want, but for flat universe. Okay, if you want to do the GR, we'll do very quickly the Newtonian. Why can we do Newtonian on scales that are of galaxies? First of all, galaxies are non-relativistic. But we're not galaxies here, we're billions of galaxies. We're scales where every point is a galaxy. Well, it turns out that as long as we keep the scales that are very large compared to a galaxy, containing many galaxies, and homogeneous, but small compared to the evolution timescale, which will drive, then we're fine. Because the main limitation of Newtonian gravity is that it has infinite speed. While in Einstein's gravity, the speed of propagational gravity is finite. But if the galaxies, if we take a small patch, bigger than these things, but smaller than the size when the finite speed of light becomes important. Okay, it's billions of light years, but compared to what? In physics, you cannot say, oh, it's really big, the light takes millions of light years, wow. No, compared to what is it big? The time. It becomes comparable to what when we say that the finite speed of light will ruin our Newtonian equations, and we have to go to GR, a much more global interpretation. But we'll assume it's small enough, we'll assume here we can do that. So there's fast communication and a local frame. Okay? And because of isotropy, because of the homogeneity, we can assume every point in the universe is a center. So let's take some arbitrary point. And because of isotropy, we can imagine our thing to be a sphere, our patch. Okay, and we're fine. Now all spheres will conserve the homogeneity and isotropy because of gravity timescale being scale independent. So all of them will evolve the same way. And because they all evolve the same way and scale independently, if we start with homogeneity, isotropy is concerned. So all patches will do the same as our patch. So we're fine from that point of view. Our only problem is how big that patch has to be. For isotropy and homogeneity, first of all, to be nearly true, and second, for the Newtonian theory not to break down. We have to make a compromise. We'll see how that comes about. Okay? So we can imagine that we're taking this patch here and expanding it like that. And it doesn't matter which patch. Right? We use so what's the gravitational field of a sphere? Who knows Gauss theorem from electromagnetics? Electrostatics? I don't know. They know Gauss theorem. Okay, so Gauss theorem for gravity is this. F dot dA is 4 pi r squared F because it's normal. This is like, for example, the Earth, and this is the field normal to the Earth, the gravitational field. So it's simply the area times F, meaning F is like that. And this is the mass of the Earth. For example, I'm giving the Earth as an example. But what applies to the Earth applies to our patch. Because it's a homogeneous sphere and the Earth could be approximated as a... In fact, this doesn't need to be homogeneous. You know, Gauss theorem applies even... This is the mass enclosed by the Earth, and this is the radius. Okay, so this is Gauss theorem. So it behaves, the field behaves as if it's a point mass in the center. Because if the Earth was a point mass in the center and we are here, this would be the same. So the field behaves, Gauss' law or Newton's law, it's before Gauss, but I did it by Gauss because you guys seem to find it easier. This is called the Newton shell theorem. Another way you can prove that is, I don't know if you take that also in electrostatics, is divide the shell, the Earth into shells and the shells into rings and add them up and integrate them much more difficult. Yeah, but you can do it. It's an exercise. This is called Newton's shell theory. Integrate all the shells and so on, and the elements, and you get it. Okay? So, bottom line, the field behaves like a point mass in the center. Of the Earth, of the patch, and so on. Now, what's the field outside? Now, we are here. How do the shells outside contribute? They don't. Because basically what this says is, because this is like Olber's paradox. I mean, this goes like r squared. If we have r1, r2, this goes like, this area goes like r squared, and the field goes like 1 over r squared. And the density is constant in both cases. And so if I take patch delta r, it will be delta r times r2 squared over r2 squared. So it goes to R2, and the same for R1. So, بيعادلوا بعض, right? So therefore it's only all our patch, the gravity on the surface of our patch, cosmological patch, or the Earth patch, or whatever patch you have, is simply like a point mass, the gravity field of a point mass in the center of the patch. Okay? So our equation is actually quite simple. This is the equation of motion of the patch. This is quite simple. This is Newton's law, and this is the mass constant, because it's a mass only inside. We don't care about what's inside. And the mass inside is conserved, like a point mass in the center, like we said. So this is a constant, and this is changing according to Newton's law. F equals ma. A is on the left and F is on the right. M is assumed to be unit mass. Okay? All this is for unit mass. Okay? Unit test mass. Okay? On the surface. Right? This allows for an energy integral. Who knows what this thing is? When you integrate this thing, this is trivial. This becomes 1 over r, right? But if you know, right? So on the left, you can say that this is like d by dr by dt squared. You know this trick? Okay? So once you do this trick, you get the energy integral. This is called an integral of motion. That is an energy integral. The simplest case of time independence of the field, and it's a very simple case of Dalton theory. Very trivial. Time invariance leads to energy conservation. Because our potential is not explicitly dependent on time. You get an energy integral. Okay? This is an important thing. So, right? So this is like a ball thrown up. And this energy determines whether the ball goes up, it's a satellite, or the ball comes back down. Energy, the energy I start with. The ball can, in principle, لو عندي مدفع يعمل قوي زي جوليus Verne when the trip to the moon, he had from Florida, and he knew that Florida is the best place to do that. A very large cannon, مدفع كبير جدا يودي الناس الأرض. Okay, so you can do it. Right? So you can do that. In this case, you have negative energy. Positive energy, it will come back. Zero is marginal. And this is how the Friedman universe is basically with matter, normal matter, no radiation, no exotica, no dark energy, behave. They can expand and recollapse, they can be marginal, or they can expand forever. The marginal expands forever also. It stops at infinity. Okay? So, and you can play with this. Put this zero here and check the time scale. You'll find it to be the dynamical time of our. Put it, try it. So let's do this a bit more like what we do in cosmology. We had R here, and it's a scale. Can we do it scale free? Can we take the radius out? And this is important because in cosmology, we just don't do one sphere. We need to do all the spheres, are they really all the same? And that's important. So let's say we take this R of a Newtonian thingy and replace it with a scale factor and an arbitrary Rs. So we are not bound by the radius of our sphere. Because we want to do cosmology, we want any sphere to behave like that, not one sphere. Right? So you put it, you'll find that it's scale-free. That's why you get these things. The dynamics are again scale-free. And that's why we can do all this stuff, because the dynamics do not depend on the scale. And you'll find that you get your energy equation again, this thing, but you divide by Rs squared. Now what is this energy, and what is this Rs squared, and what is it? Why is it the same for all spheres? Will turn out to be very interesting. Why is this constant of motion, this constant of integration, which in Newtonian sphere orbit is the energy, but here is energy divided by Rs squared, the characteristic size of the sphere, is a constant for all spheres, and we are left with a scale factor, and this fundamental constant that is not a constant of sphere, but the constant of our universe, or of any universe, described by the methodology we talked about. Okay? Now, okay, so we said there will be different types of universes. For normal matter or radiation, we'll speak about matter and radiation tomorrow, the difference between, you can also have, a universe dominated by radiation, for example. And, but for normal matter, the matter that is, and also radiation, but not the exotic stuff like cosmological constant and so on, which we'll discuss on Monday. You have these three types of solutions, which are always, at the present time, let's say here, very similar, not very far from a line. So we can always define what people call the Hubble time. Hubble time is a function of the Hubble parameter. The Hubble parameter is defined as A dot over A. Okay? So it's a logarithmic derivative of the scale factor. The scale factor, which was defines the scale-free expansion of the universe. Once we took our R and made it our SA of t. A dot over A is the relative expansion rate compared to the scale factor. So it's a logarithmic derivative, it tells you the relative rate of expansion. So if you plot these things, it will be the derivatives of lines here. And it will give you an approximate age for these sorts of models, the ones expanding the matter or radiation in them, or recontracting or things like that. It will give you the characteristic age. And this is in general physics. You can always do characteristic age by saying, if I keep on extrapolating the expansion rate today times a given characteristic age, when would I double the size? That's what a logarithmic derivative or exponential means. When do I double the size? Right? So the Hubble time is, given the current expansion rate, the universe to double its size. Right? So it tells you something, double its age. It tells you something of the time scale of expansion. And it turns out then that if I want my Newtonian, and this is called the Hubble sphere. Hubble sphere is within this Hubble sphere, the communication speed of light is much less, than the age of the characteristic time scale of expansion. So therefore, I can use my Newtonian approximation, because the time scale of light, communication, how the galaxies talk to each other through gravity, is much faster than the characteristic time of the dynamics, of the changes in my equation. If the time scale of communication is the order of the time scale of changes in the dynamics, then my dynamics is wrong, because I'm assuming infinite speed of communication. Otherwise, when my patch is small enough, the time scale of communication, even if it's in hundreds of millions of years, is still much more smaller than 14 billion years. Therefore, the change in the dynamics occurs at a much smaller scale than the communication speed. So they have time to communicate and produce the Newtonian dynamics, and the GR corrections will be relatively small. If, on the other hand, my patch is so big, and this is the Hubble sphere horizon here, to be similar to the Hubble sphere horizon, there are different definitions of the horizons, but this is one commonly used. And for normal universes, the definitions are more or less the same. Normal meaning not like the definition. The definitions can be different. Okay, for these universes, so therefore I want my Newtonian patch to be much smaller than the horizon. But this is okay, because this is, for example, if we do a Newtonian simulation, this is already a few gigaparsecs. This is very large. And my Newtonian simulation will be fine, except for percent corrections at the horizon scale, which you don't see well anyway, because it's near the horizon, so you don't see much of it. So our approximation is then fine. Right, so next, tomorrow we'll speak a bit about how you do things relativistically. But I'll stop here today, just to find the Newtonian. But there are things that you cannot do in the Newtonian thing, at least not rigorously. For example, including relativistic particles and radiation, so we do it semi-relativistic tomorrow. If you want to include the relativistic particles, you cannot do that. Or if you want to test general relativity itself, you cannot do Newtonian, obviously. You need to test general relativity and its quantification. Except if you're in a galaxy, because in a galaxy, general relativity will break from the other side. If general relativity is required in a galaxy, it breaks actually from the low acceleration limit of Newtonian gravity, not the high. So therefore, general relativity cannot be a solution to dark matter and galaxy, because these things are actually ultra weak field. It will be mean the break of Newtonian gravity from the low force, low acceleration, not from the relativistic. Here, you break from the relativistic side. You break when the things become so large that the communication time becomes important relative to the changes in RW and R. Okay? So I think that will be it for today. Any questions? No questions? Everything is extremely clear? Okay, good.
Yesterday, like, first it came to inflation. I explained why